In the test run, the certain car accelerates uniformly from 0 to 24.0 meters per second in 2.95 seconds. So what is the magnitude of the car's acceleration? How long does it take the car to change its speed from 10 meters per second to 20 meters per second? And will during the time always be able to change the speed? Uh, Explain why. So let's see this problem. Let's make a similar approach. Let's use a similar approach. So we have here a sketch. There's a sketch what is going on, so we can figure out very easier to know how to solve the problem. So we have a car here. Okay, and our car is going to accelerate from 0 meters per second, so the initial speed here is 0 meters per second, to this other position, now the car will be with a speed of 24 meters per second. How long it takes for the car to go from this speed of 0 meters per second to 24 meters per second? It takes a time equals to 2.95 seconds. So how long it takes? Let us represent the time in only one direction. But the time is not a vector, of course. But the time is just transcurrent in one direction, so we cannot go back in time. So it takes 2.95 seconds to go from one point to the other. So the first they are asking here is what is the magnitude of the acceleration of this car. So again, it's always the same process. We say unknowns, equation of kinematics that combine the knowns and the unknowns. So here we have unknown acceleration. We know the velocities, initial and final. We know the time. So if we review our, formulas of kinematics, we have this formula that say that the final velocity is equal to the initial velocity plus the acceleration time. So we know that in this case, the initial velocity is 0. So we have the final velocity is equals to acceleration time. So if I divide this final velocity by the time, it would be equals to the acceleration. So acceleration will be 24 meters per second divided by the 2.95 seconds that it takes, the altitude divided by the 2.95 seconds that it takes, the altitude go from 0 to 24 meters per second of velocity. So the acceleration, the magnitude of the acceleration will be 8.14 meters per second squared. The object is accelerating, so the acceleration vector is in the same direction that the variation of velocity. It's in the same direction that delta v, because delta v is that means the velocity is increasing. So this is our value of acceleration. Now later they say how long does it take the car to change its speed from 10 meters to 20 meters per second. So now they just change basically the problem, and they say wait, now this scenario is going to change. Now we have the car already moving at 10 meters per second. At some point here, the car is now moving at 10 meters per second. At some point here, the car is moving at 20 meters per second. I want to know how long it takes for the car to go from this point where it's moving at 10 meters per second to this point where it's moving at 20 meters per second. We just do my diagram. And what I want to know now is just time again. Not again, just the time. Just before when I want to find was the acceleration. Now I know the acceleration of the car. And the acceleration that I calculate here is now constant. So it's just a motion with uniform acceleration. So now I have one more value that I know, that is acceleration. And it's a 0.14 meters per second squared. So what formula we're going to use? Exactly the same formula, but in this case, we have no velocity equal to 0. So we say v sub f equals v sub 0 plus acceleration time. We subtract v sub 0, so v sub f minus v sub 0 is equals to acceleration time. I want to find the time. So we divide by acceleration. So the time will be 20. This is 20 here. So it will be 20 meters per second minus 10 meters per second over the acceleration. There is 8.14 meters per second squared. And then we analyze the time that takes the car, to go from this point where it's moving at 10 meters per second to the point when it's moving at 20 meters per second. We have this time is 1.23 seconds. This time is 1.23 seconds. It makes sense, right? Of course, you always have to evaluate, if the results you get make sense or not. This result makes sense. Why? Because, of course, the time from 10 to 20 needs to be lower than 2.95. It is lower than 2.95. If you get a number here that is greater than 2.95 seconds, you should realize then in that case that there is something wrong. Because if going from 0 to 24 meters per second it took 2.95 seconds, to go from 10 to 20 meters per second, you have to take less time. So you don't know the value when you make this quick analysis, but you know that it needs to be smaller than 2.95 seconds. Let's see the last question. They say, will doubling the time always double the change in speed? Explain why. Well, let's see how we can analyze this. When we have questions like this, about how change quantity with the change of another quantity, it's always a good idea to use the formulas below, and to represent the change of the variable to see how it impacts the other variable. So we have v sub f equals v sub 0 plus at. Now they say will doubling the time always double the change in the speed. So change in the speed, I will be subtracting v sub 0. So vf minus v sub 0, that will be the change in the speed equals at. So we say that this is delta v equals at. Now what they say, if you double the time, that will double the speed. Well, that will double the time. So we say that I have a time t prime that is equals to 2 times the time t. And then I can say that my new variation of velocity, delta v prime, is equal to a times t prime. Now, what is t prime? Is 2t. So delta v prime is equals a times 2t. So delta v prime, if you rearrange this, is going to be 2at. At, we know that is delta v, so now we have that delta v prime is 2 times delta v. And as you can see, know, when we double the time, that is what we did in this step over here, we will double, the change in speed. So we can say that yes, when we double the time, we double, let's say, proportion, the change in speed. Right? There is a linear direct relation or direct proportion between the time and the